Hi, my name is Andrew McLaren. We're going to talk about work and how it relates to problems like this, where we have a force that's being applied on a slope, and there's this really nasty equation. I really don't like this one, but you can understand it if you look at work in a more broad sense. And there's some weird stuff with what we're doing with Q here. I don't like it. Why Q's on this side and work is on that side. They're like on opposite sides, and it doesn't really make sense here, but they're showing that there's energy being conserved and there's some work being done with this equation. I do have this problem all worked out, so you can kind of see that explained in a little bit of the problem. I'll go through like all the steps really that are involved here. But before we do that, we need to talk about work just broadly and generally. And a lot of people think work is related to just energy, but work is technically related to kinetic energy. So if we have like a positive change in kinetic energy, like if something speeds up, then it has had positive work done on it. So there's energy entering the system, or I should say kinetic energy is entering system when we have this positive kinetic energy. So you could have a ball that's having some force that's applied to the side, and that's going to be over some sort of distance. And so you could actually get the work also by doing some sort of force times its distance. And so if you have a positive force over a positive distance, that will cause it to speed up, right? And then vice versa, if you had a negative force over a positive distance, it's going to actually cause things to slow down. So this is slowing down, losing your kinetic energy. That's another way of thinking about this. So if there's a ball that's moving sideways and then there's just friction that's being applied to it, that would do negative work. Therefore, it would slow it down and cause a loss of kinetic energy. So work is really relating to speed here. So when we're talking about work in the context of this problem, there's some work that's being done on this object by this force that should be speeding it up. So it's kind of like putting energy into the system. But there's actually friction that's kind of causing this. It's like a negative force in the positive direction because this object is going up from like here initial to here final. So there might be some force friction. It's like a negative number, even though it was a positive change in x. So that q is going to slow things down. So this problem is basically saying, oh, you're adding some work to the system. There's some work that's being lost due to that friction. And so they've kind of got those on those two sides of the equations. And you could also think about this like, oh, at first I have like no kinetic energy, and it's like all potential energy for whatever height we're at here. And then ultimately, we still have no kinetic energy, but we've got a lot more potential energy. But this change that we have here in the energy is related to some force that we've been putting energy in and some friction that kind of takes it out. So you can include that. So you can kind of say like this plus that is equal to the final. But then now you've got like work that's a positive with the reactance. And then you've got Q, which is kind of like on the other side. Or you could have it as a negative number on the left side. So it's kind of weird what's going on in that equation. Let's try and wipe our brains of that equation for just a little bit longer and think about if you have a ball that's just being dropped, it's going to have a negative force, but also a negative change in x. So you can be like, oh, there's some ball that's being dropped here. And you could consider that a negative force and a negative change in x. So it actually has positive work done on it. So because it's going to speed up. And you can think about that as that force of gravity just being a negative and that change in x also being a negative. We can do this with change in y as well. Change in x just kind of means some distance. And then also there's this thing where you can more broadly say the force times the distance times the angle between them. I believe that's going to be cosine, because if cosine of 0, that's going to be equal to 1. So if these things aren't perfectly lined up, you basically take the vector. So you could have like some force that's being applied as something moves along this change in x. And then its vectors is basically the force that's being applied. So you could have the change in x times the force times cosine theta, but that's basically the same as f of x. So you can think of rearranging our work formula that we have right here and kind of like substituting this in and looking at the vectors and saying, well, that vector went this distance, so I could use that instead of doing a cosine, which is pretty important for what we're going to talk about next in terms of what's going on in these formulas. So that's the basic idea with work. Also keep in mind there's one other situation where, like, if you are like walking up some steps and you've got some ball that you're carrying, right? There's some person that's carrying this ball and they're bringing it up to like here. And this was its initial position. So you may have caused a increase in the energy and the potential energy, but there was a force of gravity that's like down. And then there's also this force that you're applying up. And they're canceling out. So the amount of energy that you're plugging in is the amount of energy that gravity's taking out. And so that's why the energy plugged in is not like kinetic energy, it's potential energy. So you basically haven't done, there is no net work. So you could say the sum of the work is 0, but like the work of gravity would be, let's say maybe negative 10 joules, and the work of applied was positive 10 joules. So it's like you've done plus 10 joules of work, but gravity has done negative 10 joules of work. But now it has 10 joules of potential energy, which could then turn into potential energy. So the work is kind of weird because it's creating gravitational potential energy, but it's kind of indirectly. That's an important element that I wanted to point out here, is that work can create potential energy, but it's kind of indirect. So this problem is really complicated, but long story short, you're speeding up this object as it goes up the slope. They're not quite balanced. We do know that it gets sped up because it has some speed. So there's some context here that they've told us. So we can say like these forces, if we're looking at the forces in the x and the y, that the x isn't quite balanced. There is unbalanced forces because there was that acceleration over some distance. And we can look at that amount of work as the change in the kinetic energy. So this K1 and Kf, that difference. There's also some change in potential energy, like some of the energy that we're putting into the system is going to speed, some of it's going to making this thing higher up. So it's kind of similar to the situation where the amount of energy put in by your applied force is equal to the negative work done by gravity, so they kind of cancel each other out. So there's some work that we're doing here which is being canceled by gravity, and some work that we're doing that isn't being canceled by gravity. So it's kind of complicated and kind of weird, right? And I don't like this one formula because it is essentially you're just plugging in some values, but it's like how or why or what are the values, and it's kind of confusing. So I wanted to help you understand this in a different context. So there's one way to look at this, and another, the way that I look at this is really the work net, which is related to the sum of forces. And this is essentially a way of showing that the work net is like this work on this side, and then you've got some potential energy that's being taken out and some friction that's also being kind of taken out by that work. So we've put in work into the system, that's positive change in its kinetic energy, but gravity is kind of taking some of that away, so is friction. So those are kind of like negative numbers in my head. And you can think about that as why they're on the right side of the equation when we're relating these two things, and this being on the left side of the equation being a positive. So you can look at the amount of potential energy and kinetic energy in this situation and kind of like plug in some of the numbers. And you can see that the final, there's some energy there. And we also have the kinetic energy that's initial. So we have our Ki1 number. Now the force applied this is kind of weird. You can either consider this to be the force sideways, the 600 newtons times whatever distance that would be, because we had the distance going up the slope, but not sideways. So if we want to go just along the slope, you need to use the force that's going along that slope. Or you can use the 600 newtons and the whatever this number is. It would be smaller proportionally. So that's also related a little bit to what we were talking about here with the forces and the cosine. So if you need to rewatch that part, you might want to go back and see what I said about forces. And basically you can have that work component there, and then you also need the friction times the distance that friction is applied by. So if you can get that force of friction, which I believe we did, just kind of in this problem, we got the force of friction from the normal force, and the coefficient of friction, I believe, was right there. And so I was able to say what the force of friction was along the slope. So it was times that distance. And it's kind of weird, but you want that to be, in the context of this problem, like a positive, with it being on this side of the equation, but it's really negative if you were to think about it in terms of like the net work, because it kind of slows things down. But again, we're putting that on that side of the equation. So the way I think about it is really this number minus those two numbers would be the change in your kinetic energy, which would be related to your work. So this is basically the change in kinetic energy, because or related to that, because this was the initial and that's the final. So I was watching the video and I thought this was almost clear, but not quite. So I was thinking about with gravity and the work done by gravity, how that is oftentimes taken into account for with the gravitational potential energy and that change, aka the mgh they're used to calculating. And yes, you can calculate that force times that distance, that height that it's being applied by. Or you could apply the force component in the x component here, this force of gravity that's along this slope, and have that be multiplied by the 3 meters. And so you can kind of see that you're kind of either making the height shorter with the bigger force, or you're making the force shorter with a bigger length. And it really all has to do with this cosine 30. You're either multiplying f of g times cosine 30, aka making fgx times x, so it's kind of like in line with each other, or you're doing cosine 30 of the change in x, which would then give you the h. So you're kind of doing one of the two things, and they're really the same. And so you can look at like a force and the angle and all that, and understand that this is why we use the MGH, is that it accounts for this f of g along any distance. We don't need to know what f of gx is or the distance. We can just kind of plug in the height, which is pretty easy most of the time. And then you can solve for that final velocity because we also have the mass. So that's like how you use that equation. But how I really think about it is more like, okay, let's think about the sum of forces and what's going on. There was this applied force, positive, negative force and friction and gravity. So those are negative. So you could look at the sum of forces in the x direction and say, like, let's just multiply that by the change in x. And if there was some acceleration, we've done proportional amounts of pushing with forces, and we have that proportional change in that velocity, aka change in kinetic energy, which is work. So that's another way of thinking about it, where it's like, oh, okay, well, we've increased our kinetic energy by that amount because, we were pushing on it hard, but friction and gravity were taking away from it, kind of slowing it down. So we put in that much energy. We had this much energy. So the final energy is the same number as what we got um, here. So you could imagine plugging that in and solving for this final velocity as well. So you can kind of see that what's going on here is it's a weird way of writing out um, the related parts here, where you have the change in kinetic energy that's kind of being shown by the loss of gravity, which is, this change in potential energy. That is essentially what we're doing in these equations, is saying how much energy is being taken away by gravity, and therefore you don't have that available for kinetic energy, right? So you can kind of think about that in terms of the things and how they're related, and should see that. All right, I think that's the main idea. This stuff is really complicated and easy to get your brain twisted around with. Um, and so basically, just keep in mind that the force should be with the change in x. So if you wanted to do a force along the slope, you need to do a change in x that's also along that slope, and then that's totally fine. Like that force friction, I think it was actually the force friction was going negative, but it was in line with that slope, so you can just multiply those two numbers. You don't need to do the cosine thing if they're lined up. Yeah. Thank you for joining me. This has been Andrew McLaren. I tutor this stuff, so just send me an email or contact me through Wiseant. We'll see what we can do. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wiseant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wiseant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and our social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.